In the last class, we discussed Dirac equation, in which Dirac assumed the Hamiltonian to be of the form H is equal to C alpha dot P plus n C square beta, where P H operating, or you can say H as in the operator form. This is IH cross del psi by del t operating on psi. C alpha dot, the operator form of P is minus IH cross del and plus m C square beta operating on psi. So this was our Dirac equation, in which alpha and beta are constants. In fact, they are matrices. They are not scalars but matrices. And alphas, we have seen that alpha was related to the polyspin matrices, and beta is a diagonal matrix, and psi has a 4 component, 4 spinner, as psi 1, psi 2, psi 3, psi 4. So alpha is a 4 by 4 matrix. This is also a 4 by 4 matrix. This is a column of having 4 components. So in fact, Dirac equation is a 4 simultaneous equation, differential equation, the simultaneous differential equation. Now we'll see whether this Dirac equation follows the equation of continuity or not. As we have seen that in the Klein-Gordon equation could not explain the the equation of continuity. So we'll see whether this equation satisfies or not. So so we have to find out the equation of continuity. Equation of continuity. Now we have the Dirac equation. We have the Dirac equation. IH cross delta psi by delta t is equal to minus IH cross C alpha dot del plus n C square beta operating on psi. Size is a function of space and time. Now let us consider it as equation number 1. Now multiply this equation by side dagger from the left side. So multiply equation 1 by side dagger from the left. So this becomes IH cross psi dagger del psi by del t is equal to minus IH cross C alpha dot plus n C square beta. We have to multiply here by psi dagger this side. So and this is psi. Let it be noted as equation number 2. Now take the Hermitian adjoint of equation 1 and multiply by psi from the right hand side. Take the Hermitian adjoint of equation 1 and multiply by psi from the right hand side, So this will be IH cross psi by delta t, and dagger of this Hermitian adjoint of this, but multiplication of psi, and this side will be minus IH cross C alpha dot plus n C square beta Hermitian adjoint of this whole thing with multiplication of psi. Now this psi dagger will make minus IH cross, this I will become minus, and a dagger will come appear here, so this will be minus IH cross, then Hermitian adjoint symbol appear over here, and this is psi, and this will become I will become plus IH cross C alpha okay, plus m C square beta psi, and this side. Since these are constants, scalar numbers, this operation of this will not affect neither h nor c nor m nor c square. Now we know that the product, Hermitian adjoint of the product AB, it gives you B adjoint A adjoint. So suppose this as A and this as B, so this will be B dagger A dagger. So this becomes IH cross C plus MC square. This is MC square Now since alphas and betas are Hermitian, that this means that alpha dagger will be equal and beta dagger will be equal to beta. So this Hermitian sign will be disappear, and we are left with IH cross C So let us write this as equation number 3. This is 1, this is 2, this is 3. Now subtract 3 from 2. So this is 2, this is 3, subtract this from this. So subtract 3 from 2. So on the left hand side we have ith cross psi dagger del psi by del t. Take ith common. This subtracted, this minus become plus. I is taken out. So this is delta t psi. Now on this side, the right hand side, we have this subtraction of this by this. So you can take minus I cross C, take as common. Minus I cross C is here, and this will be psi dagger alpha minus of this minus sign I cross C is taken out, so this will become plus. So it will be plus del and the right next term will be mc square beta. So this will be mc square minus mc square. So this will cancel out. Here it's mc square gamma psi adjoint beta psi, and here also this is mc square psi dagger beta psi. So this term cancels out. We are left with this term only. So and the left hand side, this can be written as and on the right hand side we have I cross C oh, this is alpha. Oh, sorry. There is alpha also there. So this is alpha, actually alpha. Okay. It's all right. But okay. If you this is a product. Suppose this is a product function. First function and this of first function, and this is second function. First function definition of second plus second function definition of the first. Now this is our divergence of a vector field. Suppose this is a vector field, and this del operating on this one. This is a vector field. Alpha is a vector here. And alpha was a vector here everywhere. Yeah. Sign. Yes, this is also vector. Yes, written earlier vector sign. So this is a vector, actually a vector field psi star. This is a vector field. And we know that the divergence of any vector field, the divergence vector field physically means the flux of the field per unit volume. Suppose we have a very small volume, and the flux out of the volume is denoted by flux of F. We take the very small volume, so unit volume, and the flux of the field through this volume is denoted by divergence of A. So here we have this is a vector field, which means this is the vector field flux of this vector field. So let us denote this vector field by a symbol J. Let I cross C this is a vector field denoted by, say, it's called J vector field, and this psi dagger psi is nothing. We know that this is a probability density. So this is a probability density. So if this is a probability density, this is a probability current, that is the flux of the probability. This is quantity J is probability current. That is some flux coming out of the current volume, and this is any change in the volume with time inside. So we can write as no, H, no, it's C alpha dot I cancels out. C alpha dot this is the probability. So we can write this as d rho by dt. This is the probability density is equal to minus divergence of the vector field J, and this is called the equation of continuity. This means any change in the probability density inside a small volume is equal to the flux of the field through this small volume. So this is called the equation of continuity, and we have seen that this Dirac equation follows the equation of continuity. Now the next is to see the covariant form of Dirac equation. Find the covariant form, that is in 4-dimensional form. Dirac equation written in 4-dimensional form, in which space and time are intertwined. So covariant form of the Dirac equation. So covariant form of Dirac equation means we want Dirac equation in 4-dimensional form. So to write Dirac equation in 4-dimensional form, to write Dirac equation in 4-dimensional form, that is space and time, that is to show symmetry between space and time coordinate, between space and coordinates. Multiply the Dirac equation by beta by c. So first of all we will write Dirac equation and multiply it by beta by c. So it is multiplication by beta by c and the Dirac equation minus H cross 1 minute. So minus ith cross del psi by del t is equal to minus ith cross c alpha dot del plus n c square beta protein psi. Now multiply this by beta by c this side also and beta by c here. Bring the whole equation to one side. So we have beta by c minus h cross by delta t. So it's not minus, it's plus. So sorry, it's plus. So this, if this comes on the left hand side, this minus becomes plus. So it will be I c alpha dot del, and this become minus n c square beta psi 0. Okay. So now it multiply by beta by c each term, so it will, you will get I h cross beta. C is written like this, beta c by c t. Or take the psi will be taken out, but psi is there, psi is there. No need to write psi. So this becomes c cancels out. This will be I h cross beta alpha delta minus c cancels out. This is n c beta square and psi. Now so let us denote beta by gamma 0. So let us denote that beta is denoted as gamma 0 and beta alpha I am writing as alpha I, where I denotes is runs from 1 to 3. I 1 2 3. X comp 1 denotes x component, 2 for y component, 3 z components. So beta alpha I will be equal to gamma 0 alpha I. Let us call as gamma I. So this becomes gamma 0. This beta alpha will become gamma. So this will become IH cross and CT. CT will be x0, 0th component of the space is denoted by CT, and x1 is denoted by x, x2 will be denoted by y, x3 is for z space, x component, y component, z component, x1, x2, x3, x0 is for time component. So here we have IH cross gamma 0 delta by delta x0 plus IH cross. This is beta alpha. This will become gamma minus MC, and it's beta square, and we have seen that we know that beta square is 1, so this become 1. This equation can also be written as IH cross gamma 0 delta by delta x 0 plus IH cross summation over I is equal to 1 2 3. This is gamma I delta by delta x I minus MC. Now these two terms can be written, can be added and written in a compact manner like this. And suppose gamma 0 delta by delta x 0 plus gamma I or gamma I delta by delta xi. This is denoted as, let us denote this by gamma delta by delta x mu, where here the summation is over mu. We have removed the summation sign using, because we know the sign Einstein's sign summation means if repeated indices mu and mu are here repeated indices, the summation is over mu. So it did not write summation everywhere. So this means summation is implied here because the indices are repeated. So this side we can write as IH cross gamma mu delta by delta x mu minus MC, where mu runs from 0, 1, 2, 3. Gamma 0 delta by delta x 0 first term, then gamma 1 by delta x by delta 1 x1 plus gamma 2 and so on. So this is the Dirac equation in covariant form. And this can be written also as cross of Nabla dagger. So this is called Nabla dagger. You can write this equation in terms of Nabla dagger also. So in that case this will be equal to IH cross minus MC it's more compact. Now some property about the gamma which we have considered here, gamma. So you will see about some proper gamma matrices. Since beta we have seen that we have just seen that gamma beta is taken as gamma 0, and we know that beta square is 1. This means gamma 0 is gamma 0 dagger, and this is 1. This means, or you can write that gamma 0 is gamma 0 dagger. This means gamma 0 is Hermitian. This Hermitian property. Also gamma 0 is 1. We can write that gamma 0 is gamma 0 inverse. That is, this is unitary. This means gamma 0 is Hermitian and unitary. Now let's see about gamma i's. Now gamma I was alpha gamma 0 alpha I. If you multiply it by gamma 0 both sides, so it is gamma 0 gamma I is equal to gamma 0 alpha I, and gamma 0, this is gamma 0 square, which is 1. So alpha I gives you gamma 0 gamma I. Now take the square of this gamma I. You will get gamma 0 alpha I, gamma 0 alpha I. Gamma 0 was actually beta, so it is beta alpha I, and it's beta alpha I. And we know that alpha and beta, alpha I beta is equal to minus beta alpha I, because we had seen this equation by in the Dirac equation. While solving Dirac equation, we got this equation that alpha x beta plus beta alpha x is equal to 0, or alpha y beta plus beta alpha y 0, alpha z beta plus beta alpha z is 0. It means alpha I beta can be written as minus beta alpha. So in this equation, this can be permuted with minus sign here. So it will be minus alpha I beta alpha I. And we know that beta square is 1. So it is minus alpha I whole square. Also we know that alpha square I square is also 1. So it is minus 1. So gamma I, this means this is minus gamma I dagger, or we can conclude that gamma I is equal to minus gamma I dagger. This shows that this is anti-Hermitian. Gamma I's are anti-Hermitian, where gamma 0 was Hermitian, and you will also find that this is anti-unitary also. Since gamma I dagger is 1, it means gamma I dagger is equal to, means this is anti so we have seen that gamma 0 is Hermitian and unitary, whereas gamma I's are anti-Hermitian. And anti-unitary. Now let us take gamma 0 gamma I plus gamma I gamma 0. This means this is beta gamma I beta. So it is gamma I, it's beta gamma I plus gamma I beta. And this is beta, and gamma I can be written as beta alpha I, and this is beta alpha I. So it is beta square alpha I. This is, you permute this and we'll get the negative sign here. So it will be alpha I beta square, and beta square is 1. So this is alpha I minus alpha I, that is 0. This beta square is 1. So this gives you 1 alpha I minus alpha I. So it's easy. Now take both as gamma 0 plus gamma 0. This will be 2 times gamma 0 square, which is 2 times beta square. It's 2 times beta square, which is 2. Now take gamma I and gamma I. Plus gamma I and gamma I. So this will be 2 times gamma I, which is 2 times, and gamma I is gamma 0 alpha I. So it is gamma 0 alpha I, gamma 0 alpha I, and gamma 0 means beta. So this is 2 times beta alpha I, beta alpha I. If it's flip this beta alpha I with minus sign here, so it will be minus 2 alpha I beta alpha I. Now this beta square will be 1, so we are left with minus 2 alpha I square, alpha I, and alpha I square is also 1, so it is minus 2. So this whole gammas, equation for gammas can be written is one compact notation. This whole equation, this one equation and this second and this third, all of them can be written is a more compact form as mu gamma nu plus nu mu as 2 times g mu nu, 2 times g mu nu, where g mu nu is the metric tensor. G mu nu has components 1 0 0 0 0 minus 1 0 0 0 minus 1 0 0 0 0 minus 1. So if you take mu as 0 and nu as 0, you will get this one 0 0 0 0. This must be 2. So if you take all the components 0, so g 0 0, g 0 0 has a value 1, so 1 appears here. So it's gamma 0 plus gamma 0 is equal to 2. So it's this one satisfied. Now if you take this as 0, this as I, this as 0, or this as 0, or this as I, you will get this one 0 I 0. This is suppose mu as 1 and nu as 0, so it is 1 0 0 1 1 0, and 1 0 or 0 1 has value 0 0. So this term will be 0, and this will you get 0 here. Now if you take both as 1 1, so it is 1 1 gamma 1 plus gamma 1 gamma 1, g 1 1, that g 1 1 is here minus 1. So you get minus 1 multiplied by 2, so it is minus 2. This one, either you take 1 1 or 2 2 or 3 3, in all the cases you will get 1 1 2 2 3 3, 0 0 you will get 1. So this whole, these 3 equations can be written in more compact form. This is called relations between gammas, gamma matrices, and we know that these gammas are related to alphas, and alpha is actually a polyspin matrix, and beta is a diagonal matrix. So this much for today's lecture. Thank you.